If you're a physicist frustrated because theoretical physics nowadays seems like just a bunch of abstract math, yep, you're absolutely right. If you're a mathematician that is frustrated that arguments in physics are often vague, hand-wavy, and the math is often not precise, yep, you're absolutely right. Wait, isn't this a contradiction? Do you have too much math or too little math? How many liters of math should we use? Well, the point is to have the right math. In physics, we should only use math appropriate to represent physically meaningful objects. Physical math. If there is a mismatch, the math is too abstract, you shouldn't just ignore it like we're taught to do. Who cares? It's just math. No, we should fix it. How can we reach a good interpretation of quantum mechanics or create new physical theories without a clear understanding of what the math is physically describing and the assumptions upon which it is applicable? Wouldn't we just run around in circles for decades? In this video, I'll clarify how prevailing attitude that physicists have about math is just misguided. I'll show you an example of why it does not work and why it leads to the wrong and physical math. And that impedes progress. I'll show you how I think we can get to physically grounded mathematical definitions. But you have to start from the most basic structures, logic, topologies, vector spaces, differentiability, because correctness, meaning, cannot be sprinkled on top. That is why quantum interpretations are always going to fail. You see, in experimental physics, we have a set of experts that define units and systems of measurements, the metrology community. A mix of physicists, engineers, academic institutions, private companies, and while many physicists will find their work tedious and uninteresting, well, because they're idiots, what can I say, all the physics rests on their work. Ideally, we need a similar community for formal concepts and structures in theoretical physics. A mix of physicists, mathematicians, and philosophers that go through all the tiny math details to make sure that they make sense physically. And I understand that most people will find this work tedious and uninteresting. But someone has to do it, and it ain't getting done. And no real progress in the foundations will happen without it. So, let me show a couple of things. The prevalent attitude I find among physicists, even the ones that work on foundation, is that math is just a tool for calculations. The details are uninteresting and should be left to mathematicians. When going through technical details, I've heard, but that's just math, many times. This attitude, I think, comes from experimental physics, where a lot of issues are indeed details that do not impact the physics. How do you make your 10-ton experiment not collapse on itself? How do you structure your analysis code? How do you shield your electronics from interference? These are indeed the technical details, and you get an engineer or a technician to fix it. I think this attitude is captured in Sabine Hossenfelder's book Lost in Math, where she does complain, and rightly so, that theoretical physics is just a bunch of abstract math. She also says, but we don't develop theories by writing down assumptions and then derive observable consequences in a sequence of theorems and proofs. In physics, theories almost always start out as loose patchworks of ideas, and cleaning up the math the physics generate in theory development and finding a neat set of assumptions from which the whole theory can be derived is often left to our colleagues in mathematical physics, a branch of mathematics, not of physics. You see, these technical details are for mathematicians to think about, not physicists. And I can tell you that this attitude is completely misguided. I know so because I used to have it. And once I started working more seriously on the math and discussing things with mathematicians, it just doesn't make any sense. The issue is that we use mathematics to specify our models, not just to calculation. And specifying physical models is the whole point of physics. That's our job. It's a bit saying that you are a Chinese poet, but you don't really care about Chinese language. You will write some sketch of your poem in English to get the general idea, and what actual words are chosen, well, that's up to a Chinese expert. It makes no sense. The math specifies the physics, it's our job to specify the physics. I think this attitude is based on a fundamental misconception of how math works. That there is one true math, like there is one true law in physics. And mathematicians discovered that true math, so they are better equipped to tell physicists what to do. But this is not how math works. There are choices. Therefore, there is no single way to clean up the math. Each axiom and definition represents a choice in mathematical models. It's a physical choice. So let me give you an example. So suppose that we need to describe probability distributions like we often have to do in physics. So we have some space X and we have a probability measure, which you can also think as a probability density distribution. That's how typically physicists think about probability. So now suppose that we have a sequence of probability measures. When can we say that that sequence converges to a probability P? And this looks like just a mathematical detail. Yeah, you mathematician, pick the right notion of convergence, and who cares? The issue is that there is no single notion of convergence. There are multiple different notions of convergence. For example, we have the notion of weak convergence. That means for every continuous function f, the integral of f with respect to the sequence of probability measures converges to the final integral. That's one notion of convergence. There is another notion of convergence called strong convergence. You have your probability measure, you get an event, and now you have the sequence of the probability for that same event, and this is going to converge to the probability of that same event for the final measure. This is stronger than this, meaning that if this criteria of convergence is satisfied, then this criteria of convergence is satisfied, but not the other way around. So what do they mean physically? Well, in this case, we're basically saying that the expectation of all continuous random variables converges, and that's one criteria of convergence, or we're saying that the probability of any event converges. And somehow, mathematically, these are two different things. You might think that this criteria is enough because it's getting the expectation of all the continuous functions, but actually that's not enough to tell the probability of an event converges. So let's say that we made this choice. We choose strong convergence. Okay? Now let's have a series of probability distributions and see how it works. So we have a series of probability distribution from 0 to 1. And what happens is that these are essentially like square waves. So here you only have one cycle, here you have two cycles, and here is three cycles. So these are basically uniform distribution on this subset of 0 and 1 that becomes finer and finer and finer. And then we say that the final probability distribution is instead a uniform distribution between 0 and 1. So does this sequence of like square wave probability distribution that oscillate more and more and more, does it converge to this? Is it something that we should have or not? Does it make sense in physics? Well, let's first see if it converges strongly. So what we do, we pick an interval, which is an event, and we'll see the probability of that event as we go through the sequence and see whether it matches the final probability. So we have this interval, at the beginning we have nothing, and then when in our second element we have something, and then we get another, and again we get another, and so on. So you see that we're going to get more and more smaller peaks and valley that go inside our interval. Now the number of full peaks and full valley will coincide except at the edges. But the edges will become smaller and smaller as we increase the frequency, so the probability will actually converge because we're gonna have double the probability on half the interval, which is the same than half the probability on the full interval. So this sequence actually converges strongly. So a uniform distribution and an infinite oscillation here are the same. You can converge one to the other. And now the question is, does this make sense physically? Is this physically what we want? And you might say, well, but this is a very convoluted case. Yes, but it's something that the math will allow. And if you're gonna say, you have to make a choice of whether this is allowed in the physics or not. Does it make sense? So let me look at something else. So these are probability distribution, and we're gonna have an entropy defined on these things. Does the entropy converge in this sequence? Well, this is a uniform distribution between 0 and 1/2, and this is a uniform distribution between 0 and 1. The entropy of this is 1 bit higher of this. Now, compare between these two. We are just taking this and chop it up into two pieces. Now, the entropy is not going to change if you do that, because the entropy only cares about the height of the probability. It doesn't care where the probability is. It does not depend on that. So this has the same entropy of this. This, by the same reasoning, has the same entropy of this. So all the PIs have the same entropy, but the one at infinity, this uniform distribution, does not. So the entropy does not converge with this. And that might be something that we want. In fact, if you use an inner product to define convergence, you get a stronger criterion, which is equivalent to the convergence of the entropy. This is something that in another video I show in terms of the geometry, that entropy is geometry. Well, it also seems to define the criteria of convergence as well. So what is the physical attribute that decides what is the criteria of convergence? It's a physical choice. So choosing the convergence criteria, which ultimately means we're choosing a topology, means deciding when two objects become physically indistinguishable. Basically, what counts as an approximation in physics. And again, this is a physical choice. As we saw, we saw three different criteria of convergence. One of them makes sense physically, and the other one, no, because they were too weak. As a side note, I had finished editing this video, and I went back to my research, and I was reading this infinite dimensional analysis book written by an economist and somebody in social science. And there is this comment in their introduction on topological vector spaces. Since there is more than one topology of interest in an infinite dimensional space, the choice of topology is a key modeling decision that has economic as well as technical consequences. So you see, these two people seem to understand mathematical models a lot better than most people that I talk to in the foundations of physics. So the whole point is that mathematicians are ill-equipped to make these physical choices. And I know because they told me so. I know math, I don't know physics, I do not know what you guys want. So they will clean up the mess, but they will clean it up by making unphysical choices. Chances are when they have 3-4 choices, they will pick the one that from their mathematical standpoint is easier, more convenient and so on, which may or may not map, most of the time will not map, to what we need in physics. And so we end up with the wrong math. We end up with the unphysical math. So let me give you a couple of examples of unphysical math, things that we use every day in physics that are not quite right, and they create problems. We just got used to those problems. We don't think about them. But if we fix them, the math will feel a lot less abstract, and we would understand both the math and the physics better. So, in differential geometry, the modern way to define a tangent vector is as derivation, is as functions that take a smooth function and they give you another smooth function, which is basically the derivative along a particular direction. And so you have a basis, the basis is the derivation along the coordinate variables, and then you have components. The components tells you how much you are making the derivation along each of the variables. And this works very well in math because it gives some kind of algebraic features to the tangent space, which is very convenient when you are doing math. Except that the thing does not work with physics, because in physics we don't just have numbers, we have units. So if we imagine to have these spaces and express it in polar coordinate, we would have a derivative along the radius, which is in meters, and a derivative along the angle, which is in radiant. And you try to sum them, and these have two different units. You can't sum them. And the whole point that you have a vector space, that you have a linear space, is that you can sum things, and we can't. And it's a problem of units, it's not even physical dimensions, because if I have an angle in radians and an angle in degrees, again, the derivatives are going to be different. If you sum them, you're just going to make a mess of it. So in the same way, if we have phase space, we are going to have position in meters and momentum in kilogram meters per unit of seconds. again, we can't sum these two derivatives. And this is one of the main point, is that mathematically precise does not mean at all physically precise. So yes, mathematicians might get the jumble of the physics mess that they're making mathematically precise. They could be screwing up the physics. And if you don't understand what these details of math are, you're not even able to understand whether the physics is being corrupted or not. And by the way, this is not just a little detail. If you follow this channel, I know that I make a physical and geometrical interpretation of the action principle so that I can tell you what the action is, what part is physical, why it is that the action has to be stationary, and so on. All of that I did because I started reverse engineering all of this and making all the units work. And once you have all the physics right with the units right, you can start understanding the math a lot better. And you get a lot more intuition, because now you can use the intuition to go through the math. And the math is gonna match with your intuition. Your reasoning works a lot better. And it's one of those things that you have to try it yourself. You have to do this for enough time, and then you can see it. It's just like a shirt. You have to try the shirt on to see if it's comfortable. As long as somebody else tells you, oh yeah, this shirt is very comfortable, you're not gonna get it. So this is for something that we use a lot in physics. So the notion of tangent space we use in differential geometry is not quite right. And the thing that is interesting to me is that the notion of derivations and variation that you have in variation calculus is actually much closer to what we need. And that thing also works in infinite dimensional spaces, where a lot of the stuff that we do in differential geometry does not work. So again, the correct math from the physical standpoint is also going to give us much nicer math to work with. But let me give you another example that comes from quantum mechanics. In quantum mechanics, we represent states as elements of the Hilbert space, as square integrable function. So for example, this is a wave function for a Gaussian wave packet, and this is going to be the probability distribution that you get from that, and this is the Gaussian right here. And if you look at the probability is normalized, so the integral of this is 1. And the variance here, I've chosen it so that the variance is 1/2. Now you can also take this square integrable function. This is still a bell-shaped curve, but the tails are a little bit fatter. So the integral is still 1 because probability sums to 1, but if you try to look at the expectation of this distribution, then this actually diverges. It gets infinity because the tails are fat. Now what happens is that you can go from one function to the other function with a coordinate transformation. So you could have an observer that sees this distribution and another observer that sees this distribution. So I would see, for example, finite expectation, while you would see infinite expectation. And that does not make much sense. Much worse, you could even have a time evolution that evolves the finite expectation to infinite expectation and vice versa in finite time. And also that does not make much physical sense. And the problem is really with the Hilbert space itself, because there is a theorem that tells us that every continuous linear operator defined on the whole Hilbert space is bounded. So anything that is unbounded, like position, momentum, energy, number of particles, are not defined on the whole Hilbert space. So these operators, these observables that we need to have that define the Hamiltonians and that tell us how things evolve and all of this thing, they have these problems. And again, this tells us that we don't have the right math. So this is the current state of the art in theoretic physics. So we can imagine that we have the physical world, which is an informal system of things that we describe through experiment and so on. And we have things that we can prepare in a lab and measure, so they're well-defined physical objects in that sense. And then we have, on the other side, we have the mathematical representation in the formal system, where we would like to have well-defined mathematical objects. And then we would like to map our physically well-defined objects to well-defined mathematical objects. And the map is not going to be one-to-one because we use the same model for multiple things, right? We can use the same model for multiple electron, for a proton, and so on, right? A lot of the time the models we use are the same. But we'd like to be able to go back and forth. What we wouldn't want to have is somehow, when we are describing the math, that we make some calculation that gives us some ill-defined mathematical object, or it gets another well-defined mathematical object, but it doesn't have a well-defined counterpart in the physical world, or we have a well-defined physical object that have no well-defined counterpart in the math. Unfortunately, this is what we currently have. And from my perspective, this is very sad. I mean, how are we going to think that we can have a good interpretation of quantum mechanics, or that we're going to create these new physical laws that fix everything? This is the situation. Shouldn't we go and first fix the things that we have, and then with that knowledge, maybe we can understand better all the other things that are open problems in the foundations of physics? You see, this is what we like to have, that all the things that we have that are well-defined map to well-defined mathematical objects, and vice versa, and there is nothing that sort of goes out. And what I discovered is that if you do that, what you find is that the physical specification, you're going to have to say, well, these are the objects, physical objects that I care, and then you're going to need to be able to say, well, these are the mathematical objects that I care, so that I can have a map. And the only way that you're going to be able to make the map is that if the physical specification actually map to the mathematical definition, and you can go back and forth these things. Otherwise, you don't have the right objects on one side, you don't have the right objects of the other sides, you can't make the map. And so a mathematical definition is physical if it captures and only captures an aspect of the physical system. This is what we need. Again, we need physical mathematics, mathematics that is driven by physical requirements. Okay, so how do we make this? What standard of rigor should we have for physical mathematics? I mean, mathematicians have developed their standard of rigor for their discipline, and in physics we just haven't. So how do we make physics rigorous? And can we? And again, if you asked me 10, 15 years ago, probably I would have said, oh, you can't make physics rigorous, but actually you can. You just have to be clever about it. So let me just give you an example how we can do it. So let's say that we want to define ensembles, statistical ensembles. That's what we use in physics a lot, in statistical mechanics, but even whenever we make some experimental test. So we have this intuition that the statistical mixture of two ensembles is an ensemble. We can take two ensembles, make statistical mixtures, and lo and behold, the same thing that we get is an ensemble. Now, in physics, we are going to take this as an informal intuitive statement, as an axiom, as a starting point, because that's how it is. There is nothing else that we can do about it. It's obvious. So this is a good starting point for physics. It's precise enough for the physics, but not to a mathematician. A mathematician will tell you, well, what is an ensemble? What is a statistical mixture? Like, this is not precise. That's what mathematicians like to say. It's not precise. So what we do is we have a second part of our axiom that starts with formally and now gives us the formal requirement, something that a mathematician will find precise. Formally, an ensemble space E is equipped with an operation plus that takes a number from 0 to 1 and two other ensembles and gives you another ensembles. And this function is called mixing and is noted within fixed notation PA plus P bar B, and that P bar just means 1 minus P. I have to write that a lot, so I just write P bar. And it has to satisfy these following properties. Now, this is a formal requirement, and the mathematician is going to be satisfied because it has all the funny symbols, it uses set theory, and so on. But now we have a gap, right? We have an informal intuitive statement that makes sense to a physicist, and we have some formal requirement that makes sense to a mathematician, but then are completely disconnected. So what we need is a justification, an argument that remains in the informal world that tells you why is it that we can formalize this informal idea that the statistical mixture of two ensembles is an ensemble in this specific way. And it has to be detailed enough to give you a clear idea of what is being modeled. So this axiom captures the ability to create a mixture merely by selecting between the output of different processes. Let E1 and E2 be two ensembles that represent the output of two different processes P1 and P2. Here's P1, here's P2, these are the outputs. Let a selector SP be a process that outputs two symbols, the first with probability P and the second with probability 1 minus P. Then we can create another process B, which is the whole thing, that depending on the selector outputs either the output of P1 or P2. All possible preparation of such a procedure will form an ensemble, therefore we are justified in equipping an ensemble space with a mixing operator that takes numbers from 0 to 1 and two ensembles. So we have a clear idea of what this was in our mind. We can make a sort of a justification as to why this operation must exist. And it must exist because we are describing ensembles. And we can do this in, at least we can think that we can do that in practice, right? That we're sort of idealizing the fact that we can, in principle, always create this new process. Okay, now we have to go through and justify all those properties. We have to justify continuity. Given that mixing represents an experimental relationship and all experimental relationship must be continuous in the natural topology, mixing must be a continuous function. And of course, this might not make sense to you because this justification uses previous funding. We have a more basic idea of where topology comes in. But the point is that this is what I was saying before. We have to go at the lowest level. We have to understand what this structure means, and then we can build on top. So physical mathematics must start with the most basic structures, and then a justification will use previous funding by building on top. And so we are a little bit more on top. This is not a most fundamental structure, so there's going to be something that justifies continuity that is part of previous work. And then we can go and justify all of this. So we have identity, right? If P is equal to 1, the output of P will always be the output of P1. This justifies the identity property. 1 plus A plus 0B is equal to A because we are always selecting P1. And so the output of the whole process is the output of P1. If P2 and P2 are the same process, then the output of P will always be the output of P1 because it doesn't matter at this point. And this justifies the idempotency property. If we do PA plus 1 minus PA, then we always get A. And so on. So all these definitions now, all these properties can be justified by just the model that we have set up. And so what happens is that there is no question as to what the math describes. There is no interpretation needed because we construct the math very, very meticulously from the model that we have described. The properties are justified by or are a consequence of the model being described. So that's it. We are describing the thing. That's why we have those properties. Every that math proof then can be understood physically because since we know what all these things are, when we write a proof, we are only going to be allowed to use those properties, but then we can translate all the proofs by using the mental model that we have. And so the math describes and only describes physically meaningful concepts. It's physical mathematics. And again, I have to tell you, this is transformative because now you can go and look at the math. And the math, the proofs, are not abstract, so they're insightful. They tell you something about the physical model that you are describing. It's just so much nicer. So the goal of physical mathematics is to recover all mathematical structure used in physics from clear physical requirements. We start with the physics. And by starting with the physics, we have a clear mental model with a clear semantic. And from that mental model, we can get some physical requirements that we can then specify into axiom and mathematical definition. Therefore, the mathematics that we get, it's physical, it's physically meaningful, and we know what we are talking about. This clarifies the realm of applicability of each mathematical structure because now you know what is the model that you were assuming that told you why you could justify that math. If you're using a different model, then the justification might fail and you're not allowed to use the math. we're going to have this perfect math between math and physics such that we can go back and forth, and then we can provide a generalized structure for all physical theories, because once we saw that the statistical mixture of two ensembles is always an ensemble, that's going to be true for classical mechanics, quantum mechanics, thermodynamics, field theory, and any other theory that we're going to want to create, because that's just how we test theory, gather our data through ensembles, preparation of ensembles, and measurements of ensembles. So that's something that is going to be the foundation for all physical theories. And again, I can just say, and it might not make sense to you because you have to do it, but it's just a better way to do theoretical physics, because it forces you to think a lot deeper about the physics, the model that you're setting up, what it means to have an experimental based theory, what it means to define a state, what is the entropy or energy. These are all the things that we need to think about, and they're not just math things. Now, I don't claim to have everything worked out. In fact, I'm looking for mathematicians and physicists to help me to bootstrap this program and actually create a community around it so that we can get it. And as I said, we have to go from the lowest level of the math to the highest level of the math, clarify everything. It's unreasonable to think that I would be able to do all of this. But the main important part of this video, I want to tell you, it can be done. And all these details are not just math. There is no just math. Either the math represents physical object, then it's describing physics, and you have to understand the details of a math, because in the details of math there is going to be physics. Or it doesn't, and therefore it should be stripped away from the physical theory, and we should just get and find that particular piece of math that is actually describing physics. And it's only by understanding the full details of the math and physics and philosophy, because there is part of this understanding of what it is that you're doing is a philosophical stance. Only by doing this you can make that determination to know what math is actually physical and it's not unphysical. So if you are the kind of person that do not know what the well ordering of the real is, you're precisely the person that cannot determine whether these concepts in set theory are important. And unfortunately, the way that we are being trained, both in math, in physics and philosophy, we are trained in a very narrow way. And it's very difficult to see these connections across field. There are no journals that work across field. And so if you're looking for understanding why is it that the foundations of physics are stuck, this is it. Because the foundations of physics have to be broad, interdisciplinary, and we do not have a structure to do it. All these results are the output of my research program, Assumptions of Physics. If you are interested, you can go to our website, you can follow this channel, and if you want to participate, we also have another channel where we try to do open research online. So thank you again for your attention, and see you next time.